New York City, 1911. In a workshop lit by a single row of humming lamps, a middle-aged engineer bent over a maze of brass wheels and polished bearings. Sparks of reflected light danced across his face as he adjusted a spinning metal disc with almost surgical precision. The man was Elmer Ambrose Sperry, an inventor driven by a conviction that machines could impose order on a world ruled by chaos. At a time when navigation still depended on weather, chance, and imperfect human senses, Sperry worked toward something radically different: mechanical certainty. Sperry had already touched dozens of industries. He modernized mining equipment, built electrical systems for factories, and designed safety devices for streetcars. Yet all these successes felt like stepping stones toward a much larger idea. What fascinated him wasn't light, or electricity, or mining. It was control. He believed that the greatest weakness of early 20th century technology wasn't power, it was instability. Ships drifted off course, aircraft tumbled without warning, and artillery missed distant targets because nothing held perfectly steady. Sperry wanted to fix that imbalance. His obsession led him to a device many considered a scientific curiosity: the gyroscope. A spinning wheel that refused to change its orientation might have looked like a toy, but Sperry saw its potential immediately. If a gyroscope could hold steady no matter what forces acted upon it, then a machine built around it could achieve a kind of mechanical truth. Direction without magnetism, balance without guesswork, stability without human error. He realized that a precisely engineered gyroscope could replace the unreliable magnetic compasses that had guided sailors for centuries. For the US Navy, that idea bordered on revolutionary. Steel hulls distorted magnetic fields, storms sent needles spinning, and gunners often fired blind because their bearings couldn't be trusted. A single navigational mistake could push an entire fleet off course. Sperry offered something no compass could match: a device that pointed to true north, unaffected by metal or weather. He constructed his gyrocompass, with tolerances far beyond industry standards, polishing each surface until the wheel spun with almost no friction. When Navy officers saw the prototype hold its direction even while being shaken or surrounded by iron plates, they understood the magnitude of what he had built. The USS Delaware became the first battleship in the world guided by Sperry's new instrument, and modern naval navigation began that day. But Sperry rarely paused after a breakthrough. Solving one problem only revealed the next. Ships rolled violently in rough seas, making long-range gunnery unpredictable. Pilots struggled to keep aircraft level, especially when clouds erased the horizon. Torpedoes wandered from their intended path, wasting precious ammunition. Sperry believed all these failures shared the same root: the human body wasn't built for perfect orientation. A machine could do better. His next invention, the gyro stabilizer, attempted exactly that. By linking a gyroscope to hydraulic systems, he created a device capable of resisting a ship's roll. Test crews watched in disbelief as vessels cut through waves with far less motion than ever before. The sea didn't change, the ship simply refused to obey it. For naval gunners, this meant something priceless: a stable firing platform. Aviation soon became Sperry's new frontier. Early aircraft behaved like wild animals in the sky. A moment of disorientation, a patch of fog, or a sudden gust could flip a plane into a fatal dive. Sperry introduced his most visionary concept: an automatic pilot. A set of gyroscopes sensed every movement of the aircraft and adjusted control surfaces to keep it level. For the first time in history, a plane could maintain stable flight without constant human correction. Decades later, every bomber and transport aircraft of World War II relied on systems born from this idea. As global tensions rose, Sperry's inventions quietly spread through the American military. Submarines needed precise bearings to operate under the surface. Bombers required stable sights to strike distant targets. Battleships depended on gyro-controlled guns that could track enemies even in heavy seas. Torpedoes used gyroscopic mechanisms to stay on course. Sperry didn't design the weapons. He built the invisible systems that made those weapons accurate, reliable, and deadly. War machines no longer behaved like unpredictable beasts. They acted with mechanical discipline. Sperry's genius lay in his philosophy as much as his hardware. He didn't see technology as a tool for brute force. For him, engineering was a way to remove uncertainty from the battlefield. Every invention he built reduced the likelihood of a critical mistake, the kind that cost ships, planes, and lives. His devices didn't roar, fire, or explode. They hummed quietly inside sealed housings hidden from view. But without them, the modern war machine would have remained unstable and blind. By the time conflict consumed the world once more, Sperry's systems formed the backbone of American naval and aerial operations. Pilots trusted instruments shaped by his ideas. Navigators relied on his gyros to cross oceans. Artillery officers depended on stabilized platforms to aim at moving targets. His influence touched nearly every branch of the armed forces, even though most soldiers never learned his name. He was the engineer behind the precision of a global war, a man whose silent machines shaped the battlefield more profoundly than many weapons ever could. And so the central question emerges: how did one inventor working in a dim New York workshop end up giving the US military the mechanical stability it needed to fight a world war? Washington Navy Yard, 1914. A row of officers gathered around a long steel table as a small brass cylinder spun silently before them. The room vibrated faintly as machinery from the shipyard rumbled outside, but the object at the center of their attention didn't move. It held its orientation with an unsettling calm, indifferent to the noise and clamor around it. This was Sperry's second revolution, the stabilizing mechanisms that would redefine how ships, aircraft, and naval guns behaved under pressure. The gyro compass had proven direction could be controlled. Now Sperry intended to show that motion could be mastered as well. The ocean had always been the enemy of precision. Even the largest battleships rolled violently in heavy seas, throwing off aim, wasting ammunition, and exhausting crews. Naval gunners often fired at distant targets, while their feet slid across tilting decks. Sperry believed this was unacceptable. He saw instability not as a natural consequence of war, but as a mechanical flaw waiting to be corrected. The idea of stabilizing something as massive as a battleship seemed absurd to many officers. But Sperry didn't view the sea as a force to fight. He viewed it as a force to neutralize. His gyro stabilizer embodied that belief. The device used rapidly spinning wheels mounted on gimbals, connected to hydraulic pistons capable of countering the ship's roll. When waves tilted the vessel, the stabilizer reacted instantly, pushing back with just enough force to soften or eliminate the motion. It didn't make ships rigid. Instead, it smoothed their movements, reducing roll to a fraction of what sailors had endured for decades. This wasn't theory. Sperry installed his stabilizer aboard the USS Henderson. And the Navy watched a ship behave differently than anything they had commanded before. In rough conditions where other vessels swayed dramatically, the Henderson moved with a peculiar steadiness. For naval warfare, this changed everything. Accurate gunnery required stable platforms. A few degrees of roll meant the difference between a hit and a miss. With Sperry's stabilizer, crews could fire more consistently, reload faster, and maintain their pace during operations that previously required caution. The ocean no longer dictated terms, a machine did. Once Sperry proved stability at sea, he turned to the sky, a domain even more volatile. Early pilots flew without instruments, relying on the horizon to stay level. In cloud banks, fog, or night, that horizon disappeared, leaving pilots disoriented. Many fatal crashes weren't caused by enemy fire or mechanical failure, but by simple loss of orientation. Sperry saw a clear opportunity. If a gyroscope could hold a ship steady, It could also teach an aircraft how to remain level without a human constantly correcting its attitude. He built a gyro horizon indicator, a device that displayed the plane's orientation even in total darkness. For the first time, a pilot could trust an instrument over instinct. But Sperry wasn't satisfied with merely showing the horizon. He wanted to control it. So he engineered one of the earliest automatic pilots, a system that linked gyroscopes to servo mechanisms which adjusted the aircraft's control surfaces. In demonstrations that stunned aviation officials, his gyro pilot kept airplanes level with a precision no human could match. This wasn't automation as we know it today. It was a primitive but brilliant mechanical brain. Yet its implications were enormous. Pilots could fly longer without fatigue, navigate in poor visibility, and stabilize aircraft during bombing runs. These ideas would later become vital in the long-range missions of World War II. Sperry had effectively given aviation a new foundation, trust in instruments rather than human perception. As he pushed further, Sperry explored how stabilization could enhance fire control. Naval guns of the early 20th century struggled to hit moving targets. Even if a crew aimed perfectly, the ship's motion ruined the shot. Sperry developed gyro-based systems that allowed turret mechanisms to compensate for roll, pitch, and yaw. This meant guns could remain aimed at a target regardless of the ship's movement. A transformative leap toward modern naval fire control. Instead of waiting for the ship to steady itself between waves, gunners could fire continuously with improved accuracy. Torpedoes received similar treatment. Early models often veered off course, influenced by waves, undercurrents, or structural imperfections. Sperry engineered guidance mechanisms that stabilized the torpedo's trajectory, allowing it to maintain a straight path over long distances. In naval warfare, this improvement was far from trivial. Reliable torpedoes altered strategies, forcing enemy ships to maneuver defensively and reshaping engagements long before World War II erupted. Sperry's innovations were not isolated inventions. They formed a complete philosophy of warfare. Battles would no longer be determined by chance, weather, or the limits of human endurance. Machines could impose order on chaos, giving militaries a level of control previously thought impossible. Officers who once doubted him eventually accepted a hard truth. Technology was evolving faster than doctrine. By the late 1920s and early 1930s, Sperry's companies supplied equipment to ships, submarines, and aircraft across multiple nations. The US military, recognizing the strategic value of his work, integrated many of his systems as standard equipment. Without fanfare, Sperry had quietly reshaped the infrastructure of modern warfare. Navigation, stabilization, aviation, and fire control all advanced because of his relentless pursuit of mechanical precision. Yet, despite these breakthroughs, Sperry remained a background figure. His devices were sealed inside steel casings, hidden behind instrument panels, or tucked deep within the machinery of warships. Soldiers saw results, but not origins. Pilots thanked their instruments, not their inventor. Captains trusted the gyrocompass, not the man who rebuilt navigation from the ground up. Sperry didn't command armies, but his machines guided them. As nations edged closer to global conflict, Sperry's work transitioned from innovation to necessity. Stability turned from an engineering curiosity into a strategic asset. And so the next question emerges. How did Sperry's inventions, built in workshop silence, become indispensable tools as the world marched toward its most destructive war? Wright Field, Ohio, 1937. The morning haze lifted slowly over the airstrip as a sleek twin-engine aircraft rumbled down the runway. Inside the cockpit, two test pilots watched a cluster of new instruments glowing softly on the panel. They weren't preparing for a normal flight. They were about to test a technology that would quietly reshape every bombing raid, every long-range patrol, every night mission of the coming World War. At the center of the experiment was an idea forged years earlier in Sperry's workshop. Machines could guide humans more reliably than humans could guide machines. As aviation matured, aircraft grew faster, heavier, and more complex. Pilots could no longer depend solely on instinct or the horizon line. Weather fronts, long distances, and nighttime operations exposed the stark limits of human perception. What once required courage now demanded precision. Aviators needed instruments that did not care about fatigue, darkness, or disorientation. Sperry understood this better than anyone. His work moved from stabilizing individual machines to creating an entire ecosystem of guidance and control technologies. The heart of this transformation was the gyroscopic attitude indicator, a device that showed the plane's pitch and roll even when the horizon vanished. Unlike magnetic compasses or bubble levels, Sperry's gyro horizon didn't drift, freeze, or overload the pilot with contradictory information. It simply told the truth. Pilots trained on the instrument developed a new kind of confidence. They could fly through cloud layers, storms, and moonless nights without guessing their orientation. What once required nerve became a matter of reading a stable, trusted display. But Sperry aimed far beyond orientation. He envisioned automated systems that could assist, and eventually correct, the pilot's movements. His next advancement, the Sperry Gyropilot, was a leap forward. This early autopilot linked gyroscopes to electric servo motors that subtly manipulated the aircraft's control surfaces. Instead of reacting violently to turbulence, the plane absorbed disturbances with fluid adjustments. Suddenly, long flights became less exhausting. Bombing crews could maintain level flight for hours. Navigation errors decreased dramatically. The cockpit shifted from instinct-driven survival and to instrument-driven control. This mattered because aviation was changing. Aircraft were no longer used only for scouting. They were becoming platforms for long-range bombing. Precision wasn't a luxury. It was the difference between hitting a factory and missing an entire city. Sperry's tools became essential components of the bombsight revolution. His gyroscopic stabilizers kept bombardiers on a stable plane during release. Even minor improvements in stability meant enormous gains in accuracy. In the quiet language of instrumentation, Sperry had altered the mathematics of destruction. Meanwhile, naval aviation adopted his systems to guide patrol aircraft across vast stretches of the Pacific. Thousands of miles from land, with no visual reference and magnetic compasses spinning uselessly near metal hulls, pilots relied entirely on Sperry's gyros to hold direction. The technology didn't erase danger, but it shifted the odds. Before Sperry, long-range flight was an act of daring. After Sperry, it became a procedure. His influence extended beyond cockpits. Engineers across the military built on Sperry's principles to design fire control computers, devices that calculated projectile trajectories while accounting for wind, ship motion, and target movement. These machines depended on gyroscopic stabilization to remain accurate under stress. An unstable platform meant random firing. A stabilized one meant deliberate, repeatable patterns. On naval vessels, this increased the effective range of guns dramatically, allowing ships to hit targets they could barely see. But Sperry's most far-reaching contribution wasn't a single system. It was the integration of multiple technologies into coherent guidance solutions. A ship equipped with a gyrocompass, stabilized guns, and precision fire control instruments behaved differently than one without them. An aircraft fitted with an attitude indicator, stabilized bomb sights, and automated control surfaces became a strategic asset rather than a fragile experiment. Sperry didn't create weapons. He created the conditions that allowed weapons to reach their full potential. By the late 1930s, European militaries recognized the strategic importance of gyroscopic guidance. Germany, Britain, and Japan all raced to adapt similar technologies, but America maintained a lead largely because Sperry had spent decades refining the smallest details: friction coefficients, motor feedback loops, vibration resistance, thermal stability. His devices weren't theoretical. They survived heat, shock, and turbulence. They kept working when operators were exhausted or visibility dropped to zero. That reliability would soon become priceless. As the world slid toward war, Sperry faced an unexpected challenge. His inventions were so effective, so widely adopted, that they became invisible. Pilots trusted their artificial horizons without remembering who invented them. Naval officers used gyro compasses without thinking about the engineering that made them possible. Even Sperry's autopilot, revolutionary in its time, blended into the background of routine flight operations. The military regarded these instruments not as breakthroughs, but as necessities, tools as fundamental as the engine or the fuel tank. This anonymity didn't bother Sperry. He wasn't driven by fame. What concerned him was coherence, making sure the military understood how these technologies worked together. The future of warfare, he believed, would revolve around integrated systems, machines that informed each other, corrected each other, and collectively reduced uncertainty. Sperry's companies continued developing more advanced stabilizers, more resilient gyros, and more responsive control systems, anticipating the demands of a global conflict long before it erupted. When the first waves of war swept across Europe and Asia, Sperry's fingerprints were everywhere. In the cockpits that pierced clouds and darkness, in the guns that kept their aim despite violent seas, in the torpedoes that tracked straighter, in the bombers that held a steady line on long, dangerous missions. He had given war a new characteristic: precision. Yet the most striking part of his contribution was its subtlety. Sperry had not invented a weapon. He had not built a plane or a ship. Instead, he built the framework of stability that allowed all other technologies to function at their limits. His work didn't roar or shine. It hummed quietly inside sealed compartments, guiding thousands of decisions every second. And so a new question rises. As the world plunged into its deadliest conflict, how did Sperry's silent machines shape the war's opening battles and the strategies that would follow? Pearl Harbor, December 1941. Smoke drifted across the harbor as crippled ships leaned at unnatural angles, their decks shattered by explosions. Amid the chaos, one truth became impossible to ignore. The coming war would demand levels of coordination, accuracy, and navigation that the United States had never faced before. Long-range missions, night operations, open ocean maneuvers, carrier warfare — everything depended on instruments capable of functioning in conditions that defeated human senses. Without them, fleets would scatter, bombers would become lost, and firepower would miss its mark. The technological backbone required to survive such a conflict had already been built, quietly, in the decades leading up to that morning. Its architect was Elmer Ambrose Sperry. When the US entered World War II, Sperry's systems were not experimental curiosities. They were already woven into the structure of naval and aerial operations. Gyro compasses guided destroyers across the Pacific with steady precision, allowing fleets to navigate thousands of miles without relying on fragile magnetic instruments. Submarines operated silently beneath enemy waters, using bearings unaffected by metal hulls or shifting currents. Aircraft took off in darkness and climbed into cloud cover without losing orientation. Every one of these capabilities traced back to Sperry's mechanical logic. The belief that stability created power. Carrier warfare pushed this concept further than any previous conflict. Pilots were required to launch into unpredictable winds, return in fading light, and land on narrow decks that shifted under their wheels. A split-second misjudgment meant death. Sperry's gyroscopic indicators became the pilot's lifeline. The instruments provided a stable reference during steep turns, evasive maneuvers, and blind ascents through storm layers. Even veteran aviators admitted that without Sperry's tools, many missions would have ended before reaching their targets. Surface ships relied on his technology no less. Modern naval battles demanded that gunners engage distant enemies, while their own decks rose and fell with each new swell. The ocean did not care about strategy. It disrupted everything. Sperry's stabilizing mechanisms countered the sea's interference by preserving alignment between weapon and target. Fire control teams no longer fought the role of the waves. Instead, they trusted machines to hold their orientation. The result was a bump in accuracy that changed the nature of long-range naval combat. Destroyers, cruisers, and battleships could fire while maneuvering. A tactical advantage Japan and Germany did not possess to the same extent. Meanwhile, patrol aircraft in the Pacific and North Atlantic depended on Sperry's gyros to survive flights over endless expanses of water. Magnetic compasses grew unreliable near steel airframes and fluctuating magnetic fields. Clouds stretched for hundreds of miles, removing all visual cues. A pilot without Sperry's instruments had no way to judge pitch or roll. In those conditions, even a moment of disorientation caused fatal spirals. Navigators trusted gyro compasses and horizon indicators, not because they were convenient, but because they were the only layer of certainty in an environment that offered none. Bombing campaigns required even more precision. American strategists knew that strategic bombing would determine the outcome of the war, but high-altitude operations were plagued by instability. A bomber tossed by turbulence became impossible to aim. Sperry's stabilizing units counteracted these shifts, holding the aircraft steady long enough for bombardiers to calibrate their sights. While the Norden bomb sight often receives attention in popular history, its effectiveness depended on a stable platform. And that stability came from Sperry's gyroscopic systems. Torpedo warfare also changed because of him. Early torpedoes drifted unpredictably due to misalignment, wave action, or mechanical flaws. Sperry's guidance principles were integrated into improved tracking mechanisms, giving American submarines more dependable weapons during dangerous patrols deep inside Japanese waters. A straight-running torpedo was more than a technological upgrade. It meant submarines could attack once and vanish, instead of exposing themselves to counterattack. Even on the home front, Sperry's influence expanded. As wartime factories ramped up production, engineers integrated his servo control logic into manufacturing equipment, stabilizing complex machinery and reducing error rates across assembly lines. Precision was no longer a specialized concept. It became the defining characteristic of American wartime industry. This consistency allowed the US to produce aircraft, ships, and weaponry at unprecedented levels. Predictability in manufacturing mirrored predictability in navigation, gunnery, and flight. All of it stemmed from Sperry's insistence that machines must correct human limitations. Yet the most remarkable part of Sperry's wartime impact was how quietly it operated. There was no Sperry system emblem painted on bombers or battleships. There were no posters of him in factories, no dramatic headlines crediting his work during major operations. His technologies did not announce themselves. They simply allowed every operation to unfold with fewer errors and greater coordination. The phrase "guided by instruments" became so common that no one stopped to think about the man who had pioneered that mindset long before the world understood its necessity. To military strategists, the war increasingly resembled a vast equation. Variables of distance, altitude, ocean depth, wind direction, magnetic drift, and human fatigue. Sperry had created the tools that solved these variables. His influence stretched invisibly across Pearl Harbor, Midway, the North Atlantic convoy battles, and the bombing raids over Europe. Wherever coordination met uncertainty, his machines steadied the outcome. As the war advanced, Sperry himself grew older, but his work accelerated through the institutions he had founded. Teams of engineers refined his gyros, ruggedizing them for extreme conditions, integrating them with radar, and adapting them for new aircraft like the B-29 Superfortress. Even as new technologies emerged, the underlying principle remained unchanged. The future belonged to systems that could think mechanically, act instantly, and remain unaffected by chaos. By 1943, American officers rarely questioned the presence of Sperry equipment on their vessels or in their cockpits. They saw it as part of the natural landscape of war, not realizing that a single inventor had spent decades constructing that landscape. His devices did not make headlines, but they made victories possible. And so a deeper question emerges. How does history judge a man whose inventions shaped the war more profoundly than many of the weapons it celebrates? Brooklyn Navy Yard, 1945. Victory banners fluttered above the docks as thousands of sailors returned home. The war was ending, the world was exhaling, and America was celebrating triumph on every front. Carriers glided into port, bombers flew ceremonial passes over crowded cities, and newspapers printed the names of heroes who had crossed oceans and skies to end the conflict. Among the cheering crowds and triumphant headlines, one name remained absent: the man whose machines had guided fleets, stabilized bombers, corrected torpedoes, and held the very geometry of the war together. Elmer Ambrose Sperry did not appear in headlines, parades, or presidential speeches. His inventions were everywhere, yet he himself had vanished from public memory. Sperry died in 1930, more than a decade before his systems reached their peak importance. He did not live to see his gyro compasses installed across the Pacific Fleet, his gyro stabilizers shaping naval fire, or his autopilot logic steering aircraft through darkness and storms. But the legacy he left behind, a network of mechanical minds able to think in motion, became one of the silent foundations of Allied victory. The war that followed his death transformed his inventions from engineering curiosities into global necessities. After the war, American engineers dissected the conflict the way historians read a text, by tracing what made victory possible. They noted production capacity, strategic bombing, aircraft carriers, radar, code breaking. Yet behind all these technologies lay a persistent truth. None of them worked consistently without stability, direction, and control. A bomber without reliable attitude readings was just metal in the sky. A fleet without a dependable heading was a collection of isolated vessels. A submarine firing unguided torpedoes was a liability. When stability became a prerequisite for modern warfare, Sperry's legacy became unavoidable, even if his name wasn't. What made Sperry unusual was the nature of his genius. He didn't create one defining object, no tank, no rifle, no aircraft. Instead, he built systems, machines that corrected mistakes before humans noticed them, mechanisms that removed randomness from navigation and violence, instruments that provided truth in environments built on confusion. In doing so, Sperry blurred the line between human intention and mechanical execution. He created devices that extended perception, multiplied accuracy, and allowed militaries to operate far beyond the limits of biology. But this kind of genius rarely becomes famous. The public celebrates inventions it can see. Sperry's work lived inside sealed housings, hidden beneath steel decks and behind instrument panels. Engineers admired him, but the world moved on without recognizing how deeply it depended on principles he had refined by hand. As radar, analog computers, and jet engines emerged in the post-war years, Sperry's contributions blended quietly into the background. His name faded even as his designs remained essential. Yet the impact of his philosophy only expanded. Modern aviation, commercial or military, is built around the concept he pioneered: trust the instruments. Every cockpit contains a descendant of Sperry's gyro horizon. Every autopilot follows logic he introduced in mechanical form. Naval vessels worldwide navigate with variations of his gyro compass. Missiles, drones, satellites, and even spacecraft rely on gyroscopic stabilization to maintain orientation. Without Sperry, the modern world would still be moving uncertainly through shadows. Even the Apollo missions carried the fingerprints of his era. The guidance systems that brought astronauts to the moon relied on inertial platforms whose lineage traced directly back to Sperry's earliest controlled gyroscopes. He never imagined rockets leaving Earth, yet the heart of his work, stabilizing motion in unstable environments, became one of NASA's foundational principles. In a way, Sperry helped humanity navigate beyond the planet he had once tried to steady. The greatest irony is that Sperry's career was not defined by triumph alone. He often fought skepticism, bureaucratic inertia, and the belief that human instinct could outperform machines. Naval officers doubted his compasses. Pilots mistrusted automated controls. Engineers resisted the idea that stabilization could be engineered so precisely. Sperry overcame these barriers not with charisma or political influence, but with craftsmanship. He allowed his machines to prove themselves. On rolling seas, in turbulent air, under pressure, in darkness, in chaos. His technology didn't demand belief, it earned it. After the war, historians, attempting to map the technological evolution of combat, found a curious pattern. Sperry's work appeared everywhere, yet he was rarely credited directly. His name showed up in footnotes, engineering manuals, and patents, but not in the public imagination. Generals became symbols of victory. Aircraft became icons of innovation. But the quiet engineer who shaped their reliability, the man who gave them balance, slipped out of the narrative. This is the paradox of Sperry's legacy. He changed everything, and history almost forgot him. His genius doesn't appear in photographs of the war. It echoes inside the machinery. It's the steady line on a pilot's instrument panel, the unwavering bearing on a destroyer's bridge, the corrected drift of a torpedo, the level horizon inside a bomber shaken by flak. Sperry's presence is hidden in every moment, where motion is tamed, where uncertainty is reduced, where a machine behaves with more discipline than the humans operating it. By the time the world rebuilt itself in the late 1940s, Sperry's technologies were no longer revolutionary. They had become the baseline, the standard, the expectation. And once an invention becomes invisible through familiarity, its inventor disappears with it. Yet when historians, aviators, and engineers look deeper, the truth becomes impossible to deny. Modern warfare, modern navigation, and modern aviation all rest on a foundation that one man assembled piece by piece, gear by gear, disc by disc. Elmer Ambrose Sperry did not create the weapons that won the war. He created the principle that allowed those weapons to operate with certainty. So the final question remains: how many other architects of the modern world have been forgotten simply because their genius was hidden inside the machines we now take for granted?